Hello students, in the previous video you have seen the ideal transformers on no load. In this video we will see the how a practical transformer works. In the previous class you have seen what is practical transformer, where the iron losses are there and winding resistance are there, leakage reactances are there. So how this transformer acts with no load as well as load. First we will see when a practical transformer is connected to a no load or without loading the particular practical transformer, how it works and what are the different parameters will be there. So these two diagrams are showing the practical transformers on load. The first one is the symbolic representation and the second one is the phasor diagram. In the first one you can see there primary voltage V1 is connected to the primary winding where N1 number of turns are there. A small current I0 flows. That I0 is called as no load current, and that particular current flows through the primary coil and produces a flux phi. Because of that flux, E1 is induced in the primary coil, and the same flux phi links with the secondary coil which is having N2 number of turns, which induces E2 EMF, and the V2 is the terminal voltage at the secondary side. So you can see here in the second diagram, phasor diagram. But in the ideal transformers, what you are seeing is your I0 or your no load current falls on the direction of flux. But here it's not falling on the direction of the flux, but in between the applied voltage and the flux. So the same thing which I have explained here, the primary will draw a small current I0 to supply number one iron losses, and the second one is to supply the small amount of copper loss in the primary. So the primary no load current I0 is not 90 degree behind the applied voltage V1, but it lags between an angle below the 90 degree, means 0 to 90 degree, somewhere that current I0 falls. That same thing you can see here. See some angle phi 1 or phi naught you can take there from V1 to I naught. So as we know, without connecting any load, primary will draw a current I naught. This I naught or primary current can be resolved into two rectangular components, means one horizontal and one vertical component. So you can see here it's clearly in this figure. One is IW, another one is IM. Phasor sum of both IW and IM is taken as I naught. What exactly is IW as well as IM? See, the component IW is in phase with the applied voltage V1. You can see it in this figure clearly. V1 is in the vertical direction, the same direction IW is there. This is known as active component, or it is called as working component or iron loss component, and it supplies the iron losses and very small primary copper losses. This IW can be given as I0 cos phi naught, where phi naught is the angle between applied voltage as well as current I0. The another component IM, which is lagging V1 by 90 degree. You see in this figure, see IM, which is in phase with phi and having 90 degree with applied voltage V1. This component is called as reactive component as well as magnetizing component, which produces the mutual flux in the core. This can be given by Im is equal to I naught sin phi naught, where Iw is I naught cos phi naught and Im is nothing but I naught sin phi naught. See, what is I naught then? I naught is the phasor sum of Im and Iw, as you seen in the phasor diagram. We can write it as I naught is equal to square root of Im square plus Iw square. And if you want to get the cos phi naught, that is no load power factor, that is Iw by I naught, that is active component by magnetizing component. where W naught is given by iron losses, which we can give it as V1 I naught cos phi naught is the no load input power, or it is nothing but iron loss. During the no load condition, whatever input power supplies is equal to only iron losses. So this is regarding your transformers on no load. In the previous video you have seen the ideal transformers on no load, and now you have seen the practical transformers on no load. Now we need to see how the transformers reacts to a load. Before finding it for the practical transformers, we will analyze first the ideal transformers on load. How the ideal transformers are working on the or responding on the load. As you know the previous video, ideal transformers means there is no winding resistance, no leakage reactance, no losses. The same thing I have shown here. Only thing is a load ZL is connected to secondary side, where V2 is the terminal voltage. So the second figure shows you the phasor diagram. First we will see how it is acts. See, load ZL is connected across the secondary of an ideal transformer. The secondary EMF E2 will cause a current I2 to flow through the a particular load ZL. You can see there I2 is equal to what? E2 by ZL, where E2 is same as V2 because there is no voltage drops, because there is no resistances are present. So we can directly write it as V2 by ZL. The current which is flowing there is I2. You see here, current I2 flows through the ZL. E2 and V2 are same. Because of this current flows in the secondary, I2 sets off an MMF that is called as N2 I2. Because secondary is having turns N2, the current I2 flows in the secondary coil. That N2 I2 will set up a MMF which produces a flux in the opposite direction to the main flux phi. That main flux is originally flux set up in the primary winding because of the magnetizing current. This will change the flux in the core from the original value because of the MMF set by N2 I2, which is opposite to the direction of the original flux, which is going to disturb the value of the original flux. But the flux of the core should not change for any value from the original value. So what happens here? To overcome this effect, or to counter the MMF generated by the secondary current due to the secondary turns, primary will draw some more current from the sources, such that to develop an MMF which is exactly counterbalance the secondary MMF which is generated by I2, that is N2 I2. Hence the primary current I1 must flow in the primary side, such that there is one more MMF is set, that is called as N1 I1, which is equal to N2 I2. So we can write it as I1 is equal to N2 by N1 into I2. We can write N2 by N1 is nothing but K. We can write I1 is equal to KI2. Means primary draws more current I1 from the primary side to counter the MMF generated by the secondary current, so as to keep the original flux phi as it is. So you can see in this phasor diagram these things clearly, where initially applied voltage is V1. According to that, flux is having 90 degree lagging with the applied voltage, and same opposite direction V2 and E2 are there. This is we are taken K is equal to 1 here, when I1 is lagging with the V1. So when load is connected, current I2 flows in the secondary, which is exactly opposite direction to the I1. That's what phasor degree it is having 180 degree phase differences. So now this is what we are seeing in the practical transformers on load. In ideal transformers on load. Now we will see how a practical transformers respond to a load. In practical transformers, we will take two cases. Initially, for the practical transformers, it is assumed to have no winding resistance and leakage fluxes. And second one, with the transformer is having winding resistance as well as leakage fluxes. You can see this is the symbolic representation where a second load ZL is connected to secondary. As we are assumed there is no winding resistance, we can take E2 is the same as V2. See, in the primary side, total current flows is I1. which is equal to I naught plus Ki2. What exactly this Ki2 and I naught? I naught is nothing but no load current. Even though there is no load is connected at the secondary, primary will draw a small current to produce the fluxes. That is current I naught. When the current I2 flows because of the load ZL is connected, I naught is not sufficient to counterbalance the MMF generated by the secondary current. So primary will draw more current. That current is Ki2. Including both I0 plus Ki2, we will going to get the current I1. So the first case what we are seeing, no winding resistance and leakage fluxes. In this case we can assume that E2 is equal to V2, means there is no winding resistances. So induced EMF in secondary same as terminal voltage of the secondary, and the same thing applied voltage is equal to induced EMF in the primary side. Inductive load which causes the secondary current I2 to lag secondary voltage V2 by phi2. So the total current I1 must meet this requirement. Whatever I had told you, when I2 generates, to counter the effect, I1 must meet the two requirement. What are those two requirements? It must supply the no load current I0 to meet the iron losses in the transformer to provide the flux, and also it must supply a current I2 dash. It's nothing but we can write it as Ki2 or I2 dash to counter the demagnetizing effect of the secondary current I2. So in this case we will see how a current draws from the primary side, or to counterbalance the N to I2. Primary side I2 dash current is drawn. The MMF is such that N1 I2 dash is equal to N2 I2. So if it is equal and opposite, these two MMFs get cancelled and the original flux will not get affect anything. So how the I2 dash will be? I2 dash is nothing but N2 by N1 into I2, which is nothing but Ki2. The same thing we have seen in the previous case. In the previous case, we are taken directly N1 I1 in ideal cases, but in practical cases I0 is separate, so we need to have the I2 dash separately. So the total primary current I1 is a phasor sum of I2 dash and I0, or we can write it as I1 is equal to I2 dash plus I0, where I2 dash is nothing but minus Ki2. The minus is the symbol for it is having minus 180 degree, sorry, it is a 180 degree out of phase with I2. So this is what the phasor diagram, where we can see V1 is applied voltage, flux is having 90 degree lag with this one, and E2 and V2 are having 180 degree phase difference with the V1. So I0 is lagging to V1. When load is connected, current I2 flows to counter the MMF created by I2 and N2. In primary side, current I2 dash flows. You can see there I2 dash is exactly opposite to I2, and the phasor sum of I2 dash and I0 is given as I1. The angle between I1 and V1 is taken as phi1, and angle between I0 and V1 is taken as phi0, and angle between V2 and I2 is taken as phi2. So we can write primary power factor is nothing but cos phi1, secondary power factor is cos phi2. Primary input power we can directly write it as V1 I1 cos phi1, and secondary output power we can write V2 I2 cos phi2. This is what when in a practical transformers neglecting winding resistance and leakage reactances. In the next video we can see if we will go for the practical transformer with winding resistance as well as leakage reactance. Thank you.